In section 6.5, you had to identify real roots of polynomial equations. And in section 6.6, it's going to be very similar, but you're going to see the word all, which means you're going to be talking about rational, irrational, and complex roots. So you're going to be dealing with I again. So in section 5.3, you wrote quadratic functions given 2 zeros. In this section, you will write polynomial functions given 2 or more zeros. And in section 5.3, the given zeros were real numbers. In this section, the given zeros may be rational, irrational, or complex. So I just inserted here equivalent statements, so when you see them, you know they mean the same thing. A root of a polynomial makes that polynomial equal to 0. Or you could write it like this. You can also say that R is an x-intercept, so that's where the polynomial is going to cross the x-axis. You can say x minus R is a factor, and then when you do that, x minus R, we would set that factor equal to 0, and then you would get, adding R to both sides, R would be the root. When you divide the rule, P of x by this, so basically a polynomial by its factor, the remainder is 0. And you can also say R is a 0 of the polynomial, P of x. Okay, so let's start out with just writing the simplest polynomial functions with given zeros. One big thing to remember in this section is that irrational zeros and complex zeros, so irrational and complex zeros, come in pairs. So what that means is if you see 3 plus 4i as a 0, then 3 minus 4i is also a 0, even if it's not listed. So if you see it, you automatically have to write its pair or its conjugate down. So if you see 2 plus the square root of 3 as a 0, like I said, then you need a comma there. Then 2 minus the square root of 3 is also a 0. Even if it's not there, you write it down. Once you see this, you write 2 minus the square root of 3. That's not the case for real numbers. So if you see 4, the only root is 4. But if you see this, then you have to write that root down. All right, the first example does not have any irrational numbers or complex numbers for roots, so we don't have to worry about writing their pairs. When you're given zeros, what this means is that x equals negative 2, x equals 2, and x also equals 4. So we're going to write those first as factors. If you remember that from chapter 5, we had to write them first as factors. And since we have 3 roots, our polynomial should end up with a degree of 3. So just do 2 of them at a time. I'm going to start with these 2 first. When I FOIL those out, I'm going to end up with x squared minus 2x plus 2x minus 4, which will give me x squared, so it's just this right here simplified, x squared minus 4. Then I'm going to bring this down and multiply those 2 together. So now I have x cubed minus 4x squared minus 4x plus 16. That's my final answer. And I had 3 roots to start with, or zeros here, so I end up with, and since we talked about zeros, we're going to write it as a function. We'll say f of x equals. All right, so we had 3 roots again, so the polynomial should have degree 3, and it does. All right, now when we have these 3 roots, our polynomial is not going to be degree 3, but it's going to be degree 4, and the reason why is because this is a complex 0, and complex zeros come in pairs, so I have to take the conjugate of it. So if it's 2i is here, I have to add, so make sure you add this one, negative 2i. Now it's in pairs. Now these are real numbers, so they do not come in pairs. So we have x equals 1, x equals negative 4. So now I have 4 zeros. That means I'm going to have a degree 4 for my polynomial. All right, so let's get started. Always multiply the conjugates together, because what's going to happen when you multiply a conjugate, you should remember that the I goes away. So you don't want to multiply these 2 together and then go back with the I. It's just going to be much messier. So always multiply the conjugates together, which means now here, this is written as a root, I need to now write it as a factor. So I'm going to multiply these two together because these are conjugates, so the i's will go away. So when I FOIL those out, I'm going to get x squared plus 2xi minus 2xi minus 4i squared. Now remember that I squared is negative 1, so that's going to be a plus 4. And then these two are going to turn into 0. So that's going to give me x squared plus 4. So that takes care of this one and this one. Now I'm going to bring down the next one, which is x minus 1. And I'm going to FOIL that out. Once I FOIL that out, I end up with x cubed minus x squared plus 4x minus 4. Okay, so that took care of that one. And I still have this one, and I usually multiply it on the binomial on the left. You don't have to, but here now I'm going to distribute the x to all 4 terms, distribute the 2 to all 4 terms, and when I have that, I'm going to end up with x to the 4th for this one, minus x cubed, plus 4x squared, and then minus 4x. Now I'll go back and get the 2. Now I have 2x cubed minus 2x squared plus 8x minus 8. And when I combine those, I like to line up the like terms. So when I add, I have x to the 4th plus x cubed plus 2x squared plus 4x minus 8. All right, now we're going to go down to the fundamental theorem of algebra, and we're going to focus more on the corollary, because the corollary says every polynomial function of degree n, where n is greater than or equal to 1, has exactly n0. So we talked about that before, and that's including its multiplicities. So that means if a polynomial has a degree of 5, it has exactly 5 zeros, and that's including multiplicities. So in section 6.5, you found the rational and irrational roots of polynomial equations. In section 6.6, you will use the same techniques from section 6.5 to find all. So section 6.5, we didn't find complex. So when it says all, we're talking about rational, irrational, or complex. So to find all the roots of polynomial equations, you can use combination of the rational root theorem, the irrational root theorem, which would be the P's and Q's, methods for finding complex roots, such as the quadratic formula, or completing the square, and factoring. So those are all things that are coming back. All right, just a reminder, when you're finding the roots of polynomial equations, always try to take the GCF and factor first. It's going to make it much easier. If you can't, then you are going to have to use P's and Q's to find all the roots. All right, so let's look at our problem here. Step number 1 is you want to put that in standard form and set it equal to 0, and it already is. It's a degree of 3, so we should have 3 roots. Try to factor it. Now, some people might say, well, yes, you can factor that, but the problem is if it's cubic, so we can't do a times c to sum to b. That only works for quadratics. And we can't do grouping. So we can't factor here. The only thing that we could do is pull out a GCF, which would be 2. So the only thing that you can do is take out a GCF here. So we can pull out a 2. Then you need to identify P. P is negative 6. Identify Q. Q is 1. We want to list all the factors of P. So every number that divides P, positive and negative numbers. Every number that divides Q. And here, again, it makes it much easier when Q is 1, because basically then you just have these. So we're going to have 8 possible roots. And we want to identify all the possible factors of P over Q. So these would be our possible factors. Okay, now, do you need placeholders? And we do. Now, some of you in yesterday's assignment forgot to put placeholders in, so you weren't getting the correct answer. So always make sure you check the degrees. It goes 3, 1, so we need a 2 in there. So we got to put a placeholder in there. And we're going to use synthetic division to identify all the roots, and you have to keep continuing until all the roots are identified. So first one I'm going to have you try is 1. So go ahead and try 1. Okay, now 1 does not work because you have a remainder of negative 12. Now let's try 1. Or sorry, negative 1. We just tried 1, didn't we? Okay, so here's negative 1. When you're starting out here, you're going to bring the 1 down. 1 times negative 1 is negative 1. We add to get negative 1, multiply to get positive 1, add to get negative 6, multiply to get positive 6, add to get 0. So we have a root there. Our first one is negative 1. And then when we rewrite this polynomial, it started as a degree 3, and we found one root, so it goes down to a degree 1. And then we need to try to factor that. So we want factors of negative 6 that add to negative 1. And we can use 2 and negative 3. When we multiply, we get negative 6. When we add, we get negative 1. So factoring, because this is a 1, again, I can jump right to the factored form. And then I'll set each factor equal to 0. And I have x equals negative 2 and x equals 3. So including this root here that we found when we had a remainder of 0, we have negative 2 with a multiplicity of 1, negative 1 with a multiplicity of 1, and 3 with a multiplicity of 1. Okay, you have a couple of questions to try on your own.